Okay, now this is a problem where we have to find which object gets to the bottom of the inclined plane in the least amount of time. We have given around 4 objects. We have a solid sphere, a hollow sphere, spherical shell, a solid cylinder, and a hoop. The good thing about this problem is that they all have the same mass, which makes the problem a whole lot easier for us to solve. I've listed down the moment of inertia, and then I have listed down the moment of inertia in general based on these trends. You can see that mr square is the common thing, and then we have a constant factor. I've called that factor a in front of each moment of inertia. This will be useful later in our calculations. It will simplify the expressions a lot. Now onto the setup of the problem. Forgive the diagram, it's crude. You have an inclined plane and you have an object rolling down the inclined plane. It is rolling down like so. It is rotating about its own center of mass, and in doing so it comes down, but it is not sliding, which is to say that the point that is in contact with the inclined plane is not moving forwards. It is at rest. So as it is rolling here, this point is not sliding to, it's not coming down, it is just rolling, and in doing so it covers this distance coming down. It comes down like this rather than first a roll and something, I don't know, something like a slide down and then another roll and slide down. So it is not slipping, it's not sliding, it's just rolling down the incline. Another way to say this thing is that the point of contact with the inclined plane has a velocity of 0. So let's say the point of contact, let's give it a name x naught. So we'll say the velocity of x naught is 0. Remember that x naught is not a specific point, it is any point on the object that is in contact with the ground, or in this case the inclined plane. So as the object rolls downwards, this x naught will change, but any such x naught will have the property that its velocity at this point, when it's touching the inclined plane, then its velocity is 0. Now in such problems there are two ways to go about it. First, we can use the Newton's second law and use forces to calculate, but that is a very tedious process. It has vectors and it involves long calculations about directions and keeping in mind where each of the signs goes. So a much better way to solve such problems is to deal with scalars and use energy methods to solve. The very basic equation of energy that we have is that law of conservation of energy, and using that we can state that if all the objects start from rest at the same position, then the kinetic potential energy at the top should equal the kinetic energy at the bottom. Now the potential energy at the top is very easy, it's given by mgh, and the kinetic energy at the bottom will be of two parts. One is the translational kinetic energy, that will be half mv square, plus the rotational kinetic energy, it will be half I omega square. So translational plus rotational. The translational part is easy, it's trivial. Then you have the rotational part, and here you have to solve for I. But we know that omega is v square over r square. Omega square is v square over r square, so put that in first, and you get this expression by taking 1 by 2 v squared common. And then you can solve for v squared, and you get this equation. And when you get this equation for v squared, then you can put in the general value of I. So instead of solving for each of them separately, we'll solve them in general first and then plug in the values in them. You'll see. You'll get something like this equation. 2 mgh over amr squared over r squared plus m. I've just put in the value of I, and you can see I, r and r squared cancels, and you're left with 2 mgh over am plus m. Then you can take m out and cancel that too, and you're left with 2gh over a plus 1. Then the velocity is very simple, 2gh over a plus 1. Now since g and h are the same for each and every object, the only dependence here is on a, and since a for each object is different, we know that the velocities will be different too, and in essence no two objects will arrive at the bottom on the same time. This is the same thing, that velocity is inversely proportional to the square root of a plus 1. Now if you want to be more precise and calculate each of the velocities at the bottom, all you have to do is plug in the value for A for each case in this equation and you'll get the result. Rotational kinetic energy. The second part asks us to find out if the sphere will have the most rotational kinetic energy as it comes down the slope. Rotational kinetic energy is just 1 by 2 half I omega squared, and you put in again the value of I, A m r squared V over r squared cancels, and 1 by 2 A m V squared. Now you can put the value of V squared here too in terms of AGH, and then you will see that since A is the largest for the solid sphere, it will have the greatest kinetic energy, rotational. Actually, I misspoke. A is not the largest for the solid sphere, it's the least. Sorry, I meant least. So I'll just cut this out. It's largest for the hoop. It's 1. All other fractions less than 1. This is 1. So the hoop will have the greatest rotational kinetic energy at the bottom. Not the solid sphere. It will have the least. Okay, that's it for this problem. This is the last problem on the problem set. We are asked to solve for the rotational acceleration alpha for the cylinder. So the setup is like this. You have a cylinder like this, screw diagram, and then you have some force being applied here. I think that's the setup. Yes. Yeah. So we know that torque, we know by now that torque is just simply Fd, and torque can also be written as I alpha. So I alpha is equals to Fd, and alpha is Ft over I. And now I is 1 by 2 mr squared. It's easy, and d should just be r, the perpendicular distance. This is r, so d should just be r. And then when you plug in the values, you get alpha is equals to 2fr over mr square, or 2f over mr. Plugging in the values, you get this value for alpha, as you have correctly done so. Then you get, in the second problem, it asks if we replace the downward force by a mass. The mass is 0.6 something, but that is not needed right now. So now what's the question? The question is again to find the rotational acceleration, and we can do so, but first we need to find the force, the upward force that is being exerted here, the tension. Tension would be, in this case, mg minus ma, the downward force minus the upward force, so you get the net force, net tension, the net force, and then you get m, this is your tension. Then again, like using the same equation, I alpha is equals to Ft, we'll just put T for F, D is R, and alpha is A over R. So combining them all, you get this equation, and then putting in the value for tension, we get this. Now just manipulating the sides, we arrive at this equation, m by 2 mg minus a, or as I put it here. And solving for a, you get this, and then again alpha is just a over r, so I've just divided by r here, and then plugging in the values, you get this, as you have done so. In the last part, it asks that if the mass starts from rest, then it moves such distance in this time. Now it asks us to again calculate the new center of mass, provided that the new moment of inertia, provided that the mass and the radius of the object have not changed. What's the new moment of inertia of the cylinder? Have not changed. Object, I mean the cylinder. So they have not changed. We have the same mass and the same radius as before. The only thing that has changed is the acceleration. Well, let's find out the acceleration using the second equation of motion, or just simply a is equals to 2d by t squared. We know d and we know t, you get this acceleration. Then again, for tension,